What are you made of? The answer to this question may seem simple enough. One person might answer, well, I believe that I am made of flesh and bone, as I can see before my very eyes. While the more generalist person might answer, well, that's quite easy. I'm made of matter. And the more adventurous chemists among us would likely remark, I'm quite glad you asked. I am made of carbon, oxygen, hydrogen, magnesium, copper, zinc, phosphorus, sulfur, iron, iodine. But let's not get carried away with it. All of these answers are correct, technically, but all of these responses have a common flaw. They are all not absolute. The muscle and bone of our bodies can be broken down into cells and then into organelles. Even more so, these structures can be broken down into molecules, and these molecules into atoms, and these atoms can be broken down into protons, neutrons, and electrons. It's funny to think that even the atom, which was once thought to be absolutely whole and indivisible, can be reduced to smaller parts. But of course today, we are much more enlightened about the inner mechanisms of our universe. We now know how the fundamental building blocks of our reality, atoms, are structured. They have a nucleus of protons and neutrons and a multitude of orbiting electrons. So now that we've discovered protons, neutrons, and electrons, that's about all there is to it, right? Of course not. How arrogant must we be to believe that after only a short couple hundred years that we have completely unfurled the tapestry of reality? This, of course, raises a slew of questions. If subatomic particles aren't the end, what's next? How could we know what is the end anyways? How do we go about discovering something even smaller? Where do we start? It seems to be nearly impossible to get a grip on such a profound array of queries, but it can be done. In fact, it has been done. But what heroes do we have to thank for it? To answer this question, we will have to go to the beginning of our story. It all begins in the middle part of the 20th century, in the 1950s. Particle colliders have been around for a few years, and their scale and magnitude has been increasing healthily to allow for greater discovery in the field of particle physics. This is fortunate, however. It did lead to some unintended negative consequences for the field. Largely, the particles discovered were largely not understood due to the nature of the equipment available at the time. This led to the conception of a myriad of different quantum particles, such as bosons, mesons, baryons, gluons, and all other forms of strangely named particles one might imagine. This system of classification was dubbed the subnuclear zoo by J. Robert Oppenheimer at a conference in 1956. The phrase particle zoo is a jab at the extensive list of subatomic particles, akin to the large number of species in a zoo. One might see this and think, this model is rather convoluted and confusing, and they would be right. This system is in dire need of a fix, and luckily, there are two men suited for the job. American physicist Murray Gell-Mann, in cooperation with Israeli physicist Yuval Ne'eman, pioneered the first step in rectifying the mess created by the ever-expanding list of known elementary particles known as the particle zoo. The method developed was named the Eightfold Way, after the Noble Eightfold Path of Buddhism. This new model is essentially an organizational scheme that groups previously known particles to create a simpler and easier to understand model of the known elementary particles. Gell-Mann built off of this model to create a new system which could describe many facets of the particles we know of, including the magnetic properties of protons and neutrons. This system, however, was reliant on the existence of three new particles, which he named quarks in the spirit of a made-up word that he had read in a novel named Finnegan's Wake by James Joyce. It was in that same year of 1964 that physicist George Zweig independently proposed the same idea to the scientific community, although the particles he came up with were called aces, a name that didn't stick as well as quarks. But what are quarks anyway? How do they work? Well, Gell-Mann had originally proposed three types of quark: up, down, and strange. The types of quark are differentiated by three main factors: mass, charge, and spin. The mass of a quark is rather confusingly measured in mega-electron volts over the speed of light squared. This is a common way to weigh subatomic particles, as it leverages Einstein's famous mass-energy equivalence principle to provide a more insightful quantification of a particle's mass by expressing it in terms of the energy contained within that mass. With this being said, it is important to realize that these calculated weights are not to be taken as gospel, as they and many other properties about particles are second-hand information, so to speak. That is to say, they are too small to measure directly, so one will find that virtually all of the information we know about such things was learned by indirect observation, usually involving particle scattering experiments. Next up is charge. The charge of the quark is pretty straightforward. The charge is represented as a fraction of the elementary charge, or the electric charge of a proton, which is approximately 1.6 times 10 to the negative 19th coulombs. Last on the list of properties is spin. This name is rather misleading, as the quarks do not actually spin. This property is instead used to describe the interactive behaviors these particles exhibit, such as magnetism and gravity. This concept is based off of some models which include values for angular momentum, hence the name spin. This quantum value is largely meaningless in a practical sense and can be thought of as an accounting trick for physicists because it does not explain why the particle behaves the way it is described, it just describes the particle's behaviors. Now you'll notice that one of the three types of quarks mentioned earlier is missing from the proton model, which is the strange quark. This is because the strange quark, as its name suggests, contains a property known as strangeness. This property describes the strange tendency of a particle to resist decaying from the strong force, in this case into a more stable up quark. The half-life of strange particles is still very short, however, usually in the order of a trillionth of a second, all the way down to a septillionth of a second. Even though these particles only exist for a short time, they are still instrumental in soundly explaining the principles surrounding quarks. Now I've just shown you a model of the proton as it is commonly accepted as today, with the inclusion of two up quarks and one down quark. But this model, as well as the quark model, was largely criticized upon its proposition. The main hurdle was that scientists were confused whether Gell-Mann's quarks were a physical phenomena or simply an abstract idea to explain the behaviors of elementary particles that weren't understood at the time. This was the case until 1968, when physicists at the Stanford Linear Accelerator Center conducted inelastic electron nucleon scattering experiments that produced behaviors that were consistent with Gell-Mann's description of quarks. Since then, there have been discoveries of three other types, also called flavors, of quark. Among these are charm, top, and bottom, all of which were proposed to explain unknown decays in the three-quark theory, as well as other physical phenomena. Following these developments, quarks have since been accepted by the scientific community as a fundamental part of the standard model of particle physics. So why is this important? The short answer is because humanity as a whole is rather lost when it comes to researching this level of particle physics, and more broadly, we cannot explain why certain mechanics of the universe are apparent. For example, earlier we mentioned the spin of a quark, describing how a particle interacts with the fundamental forces of the universe. We cannot explain what makes these particles undergo these interactions. We can only accept them as they are. Furthermore, the fundamental forces, gravity, electromagnetism, strong force, and weak force, all seem to be different manifestations of the same phenomena. The reason why these forces, although seemingly one, can act so differently is one of the greatest unsolved mysteries of science, and a more intense study of particle physics could help uncover the answer. The stagnation in the advancement of particle physics can be attributed to the explosion of the field during the mid-20th century. The rapid advancement and immense popularity of particle physics led many to believe it was a solved science, leading to a sharp decline in new entrants to the field and a falling out of relevance of physics from public interest. All hope is not lost, however. In recent years, there have been a multitude of promising discoveries in the field of particle physics, largely credited to the European Organization for Nuclear Research, commonly known as CERN. It is institutions like CERN that give us hope for the future of particle physics and make us wonder what truths lie ahead of us, waiting to be discovered, and bring us closer to the reality we live in, deepening our understanding of the universe.